So our next speaker will tell us about galaxy clusters and magnetization of the intercluster medium.
Yeah, thank you. I would like to put a bit forward what we just heard about galaxy clusters, and I would even narrow it down to radio relics. The only shocks, I ignore turbulence here a little bit. I will talk a bit about turbulence. Thanks a lot for the organizers first to give me the chance, invite me to this very nice conference. I enjoy that very much, and it is really a pleasure to be here. Okay, so what are we talking about? Let me repeat. You heard that already. There are galaxy cluster mergers. You see the X-ray over here. You see these nice shock fronts. Clear-cut case. There are huge shock fronts traveling outwards, and apparently they get radio loud. And we see that with current telescopes, and we hope to see that with upcoming telescopes like SKA. So I made a prediction once for LOFA. I predicted LOFA will detect 2,000 radio relics. I think in our last data release, we detected, I forgot the number, 40 or something like that. So maybe I should revise my prediction. I'm very certain SKA will detect 2,000 radio relics, and then we have a huge number to discuss. So these are the textbook candidates. There are other clusters you saw already, Abel 2744. Here's a very nice relic, but here's also a relic. Here are also 2 relics detected. So at some point, things get a bit messy. And in LOFA data release, there was one release on the more massive clusters, Planck clusters, and there was another release on other relics which have been detected in non-Planck clusters, so the low mass clusters. And you can now look at the image over here, and so the background, the optical and contours, the LOFA image. And now please spot the radio relic. And you see that gets a bit complicated to say, okay, here is a radio relic. How do we distinguish? How do we know there's a radio relic? So from these clear-cut cases to those objects gets a bit more complicated. So what we are doing currently, so that is one work which is ongoing that we try to compile. So that there are 300 clusters with diffuse emission. So according to our compilation, there are 100-something clusters for which radio relics have been claimed. But as you saw in the images before, so these claims are at different stages. So some objects are pretty clear and others are a bit less clear. So what we try to do is to have a kind of a set of criteria from location, what is the morphology. So if we know something about the spectrum, we should take that into account. If we know something about polarization, that is something I would like to come to in the second half of my talk. Then we know something. And for some, not very many, the X-ray surface brightness jump, what you expect for a shock front, has been discovered. So the problem clearly is all these relics are in the periphery at the virial radius, where the X-ray surface brightness is low. So detecting the jump is difficult. And surprisingly, for many relics, the jump is weak. So the Mach number seems to be low, what is one of the big puzzles. So that is something what we try to do. So here's an example from Candano's Mercat Galaxy Cluster Legacy Survey. So you have the X-ray in background. Maybe contours are not very well seen over here. But if you look at the relic over here, so if you know where the X-ray is, if you know the X-ray has a merger over here, you would immediately believe that is a relic. If you look at the morphology itself, well, it could be also kind of a set of 2 radio galaxies. So that is not so easy to see. The spectral index gradient even goes into the wrong direction. Even more complicated is a counter relic over here. We still have some emission over here. So here it's a bit unclear. I think it overlaps with a galaxy. And here's some diffuse emission. I showed that a colleague. He immediately said that is a radio galaxy. So this identification of these objects is difficult. So according to our scheme, so we give some, what I'd call it, scores or credit points. So score of 5 is good, but not excellent. So it's kind of a mediocre identification of a radio relic due to kind of these contradicting features that the gradient goes into the wrong direction. Morphology is not as elongated as in these textbook cases. So therefore, if you would not know the cluster, you would be not so certain what it is. So that is ongoing. So to really look at all these objects is a bit tedious, but that will be, I think the first set will come out soon. So the one thing what we are looking into is, for instance, spectral indices. So these are features not clusters, so features in clusters, spectral index distribution. You find a nice spectral index variation over here. So the mean is something minus 1.15. So that is basically what we expect for shock front, injection at the shock front with diffusive shock acceleration and then aging. That should give something what is minus 1.1 or so. Deviations are a bit difficult to explain. So there are some relics which are much flatter. There are some relics which are much steeper. Cluster Isabel 521, which has been studied here, shows a steep relic. A known case is Zwicky cluster 0008, which really has two very steep spectrum, but morphology-wise, it looks perfect. So I would say from the cluster community, so we are far from understanding why that is the case. So there are some suggestions what happens, but that we really know what is ongoing is unclear. So that is what the compilation is good for, so that you get an idea, is there systematic? So maybe the ones we detect in the periphery, they tend to have a canonical spectrum. If we go a bit closer here to a few hundred kiloparsec, maybe to a megaparsec, you get a scatter over here. But I should make clear, so who knows about the subject, the radio phoenixes have been introduced in the past. So radio phoenixes are really deliberately excluded here. So in the past, there was kind of such a relation which was caused by including radio phoenixes. So these are objects which are clearly, more or less clearly identified as radio relics. So what I would like to do is just to say, we need higher resolution, deeper studies. So that's clearly called for a much better telescope, which can give us answers. Being back in Bangalore, I think I've been here maybe 15 years ago to a very nice conference on radio astronomy, and that is, I think, where for that conference I prepared that movie, and I think it's still a good movie, so therefore I would like to show it. So that is an animation from a cosmological simulation we did where two galaxy clusters merge. So here's one galaxy cluster and the other galaxy cluster. Here you see in a projection, the contours are X-ray. Now the two merge, and what you see is it gets overpressured in the center. And then at some point, you have the shock front over here, and then the shock front propagates outwards. And what you also see is that at the periphery, it starts to fragment. Only small fractions are luminous. And then the shock front is still there. You see it in the temperature differences. But you, what's happened here? Okay. You see that then still in the temperature gradient. So it's not that the shock front vanishes, it's just the radioluminosity goes down, then density goes down, magnetic field goes down, temperature goes down, everything goes down. So therefore, the luminosity decreases, and we are a bit in a similar situation as in low mass clusters, where everything is a bit lower, temperature is lower, density is lower, magnetic field is very likely lower. So therefore, the luminosity decreases. So what we can learn if we take a huge, so here we took 280 clusters from the 300 project and constructed light curves. So, and there we found that basically every cluster which merges create a shock front propagates outwards. And so in the massive clusters, we get a light curve like that. So after the first core passage, so then the luminosity rises. And after a few hundred of mega years, maybe almost a giga year, you have a peak in radioluminosity, and then it decreases. So that is what we find, what you expect, and where you can now calibrate and can say, where do I expect the halo? So surprisingly, not every double relic has a radio halo. And what is a bit the question is, are radio halos faster than relics, or relics faster than halos? So from that plot, so we find that in the massive cluster, so the relics last for quite a while. If you look at that animation for the radio halos, I think they start a bit earlier. But that is ongoing work. I think we have to still have to investigate that. But you also see the difference. So if we have the massive clusters, they get very luminous. If we go to a bit less massive cluster, so that is in simulation, so the mass difference is not so big. You find they are significantly less luminous. So difficult to detect, but they have the same light curve. So needs more sensitivity. So just a quick overview of some other features. So the toothbrush relic, for those who don't know, the X-ray emission is over here, the radio emission is here. maybe on that screen it's not so super visible, but believe me, the radio emission goes to somewhere out over here, and we still don't really understand. So why is there radio emission over here, which is really kind of perpendicular to the X-ray emission? So if you look at this in high resolved images, you find all criteria we have for radio relics perfectly fulfilled in this object. It has a nice gradient. We will talk about polarization in a minute. It's nicely polarized. What causes these shock front? What causes these density jumps? What accelerates the electrons really far in the periphery, far in a region, or in a region where the X-ray, where the density of the intracluster medium is pretty low, is a bit unclear. So I just introduced that, that I wanted to highlight another puzzle, what needs more studies. I think we don't understand that very well. So if you look at this toothbrush, so it has a bright emission over here, it has some emission over here, and has a rather faint emission over there. You would expect these are 2, 3 physically pretty different regions. So you would expect that is somehow different. Maybe the Mach number is different. Something should be different in the 3 regions. If you now look at the spectrum, all 3 regions over here with different luminosities show exactly the same power law. And that goes from LOFA to VLA C-band, and that has been, okay, that's not everything has been measured at highest frequencies, but the overall spectrum has been measured from LOFA LBA, starting even lower over here, and it goes up to 18 gigahertz. So it has a perfect power law, and it does not change with environment. And so it's a riddle. So we don't understand why that is the case, since we don't believe that the Mach number is exactly the same over there. What we think is, what we saw, that the shock fronts are probably have a distribution of shock fronts. So the power spectrum is maybe a result of the distribution of Mach numbers, which could be the same everywhere. That is more plausible that the average Mach number or the peak Mach number may change, but the distribution of Mach numbers you have in your intercluster medium, that may set the power or the slope of the power law or cause the power law, and that might be the same over there. But we need a better physical understanding of that. Here's another recent study which is submitted and I hope to be published very soon. So that is an LBA study. So that is now the sausage again at 45 megahertz. So LOFA LBA has studied that object. And what we find is that in the intracluster medium, you now get really a population of these fossil electrons, which are residing over there. It's not, so here's no halo. Okay, there's a weak halo in the cluster, but doesn't show up over here. So you don't see that. But you see that behind that relic, so these low energetic, relative, let's say a bit lower than what we really find in the shock front, they spread out to a large distance. So what we think is that in galaxy clusters, you really find a large amount of fossil electrons. So we try to model the surface brightness profile that goes from 3 gigahertz over here down to 45 megahertz. You get a reasonable match, so that will be described in the paper what is needed to get that, but it's not so easy. So it's not some projection and some cooling. So if you just have some projection and some cooling, you cannot really match the surface brightness profile. So maybe something is happening, maybe re-acceleration, maybe electron transport. I think so these excellent data allow much more detailed physical studies, try to get an understanding what goes on in these galaxy clusters. So that is a bit, yeah, that is where we try to measure this profile and where we try to match it. And you see that we get a much more peaked L-band profile from expected from higher frequencies. Observations are slightly different. So if you go further here, you will find that the low band is even more extended. But we also find is that there's some emission in this upstream regime. What is unclear, what causes that? Maybe some shock fronts which are a bit further out, but maybe also some electron transport, which allows the electrons to diffuse or get transported over there. So these are ongoing studies, and I find that really exciting that we can, with these high resolution and high sensitivity images, we can try to understand more physical aspects in the intracluster medium. The final thing I would like to talk about in the last 10 minutes is the polarization. The sausage is perfectly polarized. I think, again, the textbook candidate for polarization, you have the E vectors over here. They're really like needles perpendicular on the sausage. Still, after 15 years that has been released, it's not fully understood. So if you just run a MHD simulation, the shock fronts, you get much more scatter in the polarization direction. So if that is really small scale turbulence, which is compressed, it's also unclear, but the observation effect is you get a perfect polarization. If you do synthesis, you can measure what is the Faraday depth over here, so that for that particular galaxy cluster, it's dominated by the galactic foreground. You get some Faraday dispersion, which is 30 rad per square meter, so that is kind of a medium level. Maybe the cluster, maybe a little bit of foreground, so maybe a bit unclear what that is. From the Faraday dispersion, we can estimate with correlation lengths in the intracluster magnetic field. To get such a Faraday dispersion, the correlation lengths cannot be super short. What has been also found is that this partially resolved rotation measure analysis, we find that the intrinsic, so that is not the observed polarization fraction, but with the RM synthesis, you can extrapolate what is the intrinsic fractional polarization. So it's not the depolarization which happens. That is something we can correct for. It is an intrinsic polarization, and we find that the intrinsic polarization in the sausage decreases. So that has caused some debate. So what is the reason? Maybe there's some turbulence downstream. So then we try to understand that. And I think the first thing what was a bit surprising is that due to the aging in that sausage, you expect that the polarization fraction should go up. But instead of an increase in polarization fraction, if we here include some projection, we find these decrease. That can be turbulence. I have investigated that also a bit further. You can also assume, if you assume that your magnetic field is not homogeneous, that you don't have a homogeneous cooling, you also get some decrease in the polarization fraction. That is just the case that initially the region with magnetic field parallel to your surface dominates the emission. That causes your initial polarization, but these electrons also cool faster. So therefore, you reach a point, if you have an inhomogeneous magnetic field, you reach a point where your polarization goes down, and then the polarization fraction goes up again, but then the polarization direction has flipped by 90 degrees. So here we would have, we have a region where then the polarization direction changes. So currently the sensitivity is not good enough to look for that, but we could also interpret this decreasing polarization fraction as an indication that the magnetic field in the relic is not homogeneous. That is one possible interpretation. So I should come to my last point I would like to make. So that is the MAX J0717 galaxy cluster armchair radio relic. That is a pretty complex case. So I think initially that was also believed to be a very nice relic since tangential to the X-ray emission, but then higher resolution studies indicated, okay, that is an alpha-1 galaxy, so unfortunately not a radio relic, even if the morphology initially looked nice. But that complicated emission over here is a relic, so I think I skipped that. That was initially believed to be related to a head-tail radio galaxy over here, which has a tail which really bends into that radio relic. And that illustrates what makes these lives so complicated. How do we know there's a physical connection, or that is just projection? Yeah, the gradient, the spectral index gradient steepens. That is what you expect, but how can you verify there's really a physical connection? And that is what we try to do with Faraday tomography, that we know is a relic and is a tail galaxy at the same place. It's the same radial distance in the galaxy cluster. That is what we wanted to figure out with the polarization analysis. Can we separate that? Can we know if they are at the same location in the cluster or if they're somewhere different? So that is called Faraday tomography, that you try to figure out where it is. And usually it's assumed you take the rotation measure and the rotation measure tells you something about the depth in the galaxy cluster. But you might be fooled by that, since the rotation measure is an integrated property of your magnetic field, and your magnetic field may change direction. So you may have the same rotation measure located at very different positions. So one should not take that as an easy measure for distance. So that is what we wanted to do. So here's a very wideband VLA observation from L-band, S-band, and C-band. What we used for that, and then we divided that in some boxes, covering also that head tail, covering also that relic over here, and did our QU fitting, the RM analysis and QU fitting. So most of these boxes are nicely fitted by one component. Some of these boxes we find already evidence if you have only one component, it doesn't fit very well, and that is here where the head tail galaxy is located. Okay, so here there's no way, so the dashed line is one component. Here there's no way that you can fit the Faraday, the M spectrum with one component, so that is impossible. It is a bit to challenge. Okay, that is a psychedelic plot. So I just, since it took me so much work to produce it, I wanted to show it, but I'm very certain that nobody can make any sense of it. So these are all our boxes, and that here is a Faraday dispersion, and we find that that one relic, I will come to that, as a very low, about 10 sigma rad per square meter, and but others are up to 50, 60, 80, 100. And so these different colors indicate if there's one component or two components, and here is a mean Faraday depth in each of the boxes, and you see that that's scatter. So, okay, that is good, and now we want to use that. We want to use that to do the tomography. So how do we know how deep something is in the galaxy cluster? That is a challenge. And so you can plot it in a different way. And here we plot the Faraday depth. So that is Rm over here, and that is a dispersion. So how quickly does it depolarizes? And what we find is that these things are related in the cone-like structure. So yeah, so if you have for boxes or for regions where the dispersion is very low, the scatter is low. So the individual Rm doesn't help you very much, but if you look at the scatter, then you find a very nice correlation. If your sigma Rm is very low, you also get a small scatter. If you go to components or boxes where the dispersion is high, so which quickly depolarize, you get a larger scatter. So therefore, I consider the sigma M a better indicator for the depth. So yeah, if it's highly depolarized, that is probably deeper in the galaxy cluster, and we find that the head-tailed galaxy is highly depolarized. So, okay, now there's a debate: is it intrinsic or is it intracluster medium? If we suppose it's intracluster medium, so we think that the head-tailed galaxy somewhere over here, so that is then highly depolarized. So that is probably deeper in the cluster. The relic component related to it is down here. It's very little depolarized, so we think it's physically separated. Still, since we do not know if the depolarization is intrinsic or the intracluster medium, it is hard to make a very definite statement on that. So we compare that with simulation then, say, okay, that is intracluster medium magnetic field with a flat spectrum, steep spectrum. We then produce a mask of that area and say that in our shock front, as we saw in the simulation, there are different patches which emit. And that can be far away from the observer, it can be close to the observer. And if we do that, we can reproduce, okay, that is our Faraday depth yet, we can reproduce the dispersion versus rotation measure scatter. Yeah, we get exactly the cone-like structure. So that our model, what you saw in the shock front, that some parts of your shock front are very much behind the cluster and others are really towards you. That seems to be a good model to reproduce the cone-like structure in the plot between Faraday dispersion and the scatter of Rm. The question is now, and that is what we want to do, is that we want to understand what magnetic field distribution do we need to get exactly the opening cone. Yeah? So from that galaxy cluster, we get a very clear range where where the RM scattered for a given sigma m. Yeah, so the opening is roughly 1.2 here in this particular case. If we go to our simulation, so then we find that the opening of this cone depends very much on the spectrum what we use. The small scales determine the scatter, the large scale, the small scales determine the sigma, the large scales determine the scatter we have. So therefore, the ratio between the two things is a good measure of the power spectrum of the magnetic field in the intracluster medium. So that is something we are currently, so that is in progress. We currently try to quantify that, and that also depends where do you exactly cut your spectrum, where do you put your boxes on your relic, so that needs to be finalized. But qualitatively, we see this clear dependence on our spectrum of the magnetic field. So what I want to convey over here is that the polarization of radio relics are an excellent tool to measure the power spectrum of the magnetization in the intracluster medium. With that, I would like to conclude. So I would like to convey, so radio relics are cool objects to be studied. So that is something what needs to be done and should be done more often. So the classification is often challenging. So don't take that too easy. I think it has happened that very nice objects turned later on to be radio galaxies. So one should be maybe careful with that and should have a quantitative answer to that. We've showed that radio relics have a typical light curve. You have to wait a bit. It's on a giga-year timescale, but that is basically for every merger you can reproduce a pretty similar light curve. LOFA LBA observations show a very wide distribution. This is partially wide distribution of low energetic electrons. So Faraday tomography works in the intracluster medium. And from the Faraday depth versus Faraday dispersion, we get a cone which allows us to put constraints on the power spectrum of the magnetic field in the intracluster medium. Thank you for your attention. I'm open for questions.
So, are you taking this Faraday dispersion to be the main depolarization mechanism here?
It's a good question. Yeah, I think so. For radio relics, so the alternative would be that you have different orientations, so kind of a beam depolarization, since you integrate over an area with different intrinsic orientations. And I think in that sense, radio relics are perfect, since the Sussex shows intrinsically, it's perfectly homogeneously polarized. So I think radio relics are the best tool to study polarization, since we know that intrinsically, or we have at least evidence that intrinsically it's homogeneous. Therefore, I think depolarization is Faraday rotation along the line of sight.
And also, like for 4.8 gigahertz wavelength, how depolarization, like in this wavelength range, depolarization is like significant or
4.8 gigahertz. Well, I can just show what we have here. So that would be the C band. So here, I think most of the things are found in polarization. At lower bands, it's completely depolarized. But there's still some parts over here which depolarize. So it depends where it's located. So parts of that emission which are really behind the cluster still at least fractionally depolarize in C-band. Okay. That also depends on the size of your cluster. I think if you go to a smaller one, maybe less. But I think in a very massive cluster, then it may depend a bit on your beam size. I think you get depolarization.
Thank you.
Okay, we've got lots of questions.
Hello. So for the spectral index study of the toothbrush cluster, we can obviously see there's a really flat spectrum, right? But
you mean here, or the overall spectrum?
A spectral index, the next slide, yeah.
Yeah.
So, but in the local, there is, it does not show, locally it does not show a power law.
No. Yeah.
So, but for every telescope, you can see like there is some thing there. So can you comment on that?
Yeah, that is what we expect. So if you have a shock front, it injects with a power law. But now you have the entire downstream area, it cools. Therefore, locally in your downstream area, you always get a curved spectrum since you have cooling. If you sum up all these downstream spectra, you end up with a power law again. So that is, you have a power law injection, you have homogeneous cooling, you have the sum of all these. So the condition to have an overall power law is a quasi-stationary scenario. Since if you look at your downstream, for something what we see in LBA, but is really very much downstream, the shock which has passed that area earlier in time and a different region in the cluster. So the question is the magnetic field strength in that area the same as here, where the shock is currently accelerating, and has a Mach number or something of the shock changed over there. So the power law is only obtained, or the -1 power law is only obtained if we have this quasi-stationary scenario, what means the shock front, the magnetic field, everything stays the same. So you can read that as an evidence that this quasi-stationary scenario is true. So that not much changes when the shock propagates from LBA, where LBA is still visible, to where the shock is currently accelerating. So yeah, that is very well understood, but also sets conditions on what happens in the intracluster medium, on what happens to the shock front.
Final question while the next speaker comes up and sets up their laptop.
Quick question, like one is, how is reliability quantified, and little bit more? Second is, you did Faraday tomography. If you do spectral tomography and those maps, are they telling us something similar or different?
Yeah, I'm not a huge fan of spectral tomography, so therefore I comment on that first. So I think I don't comment that further. So I would rather look at spectral index maps. So I think spectral tomography is kind of take a spectral index map and subtract a certain power law, and then you see what is deeper and less deep. So therefore, I don't find that super helpful. Reliability index, yeah, we have, I do that with a few students, and so that they can analyze clusters, I really have to give very precise criteria for this reliability score. I think that is maybe beyond what I can tell over here, but we have a kind of a long list for these 8 criteria now, how to do that exactly. So clearly in future, we want that can be done automatically, so that it works without human interaction. So if you look at SKA, so when all these surveys come, so I think I don't have sufficient students to do that manually. I need a machine which is able to do that, and that is described. So we currently prepare a paper. I can tell you afterwards, or you can have a look at that publication. Thank you.
If we can thank the speaker again.